Welcome back, Professor Bright here, and in this video series we're going to look at two different tests that help us prove, or maybe conclude, convergence of a series. The integral test and the comparison test. Now actually there's two comparison tests, we'll get there. Also in this section there is information about error estimates and remainder estimates for series. If we sum the first 100 terms, how much is left. Very interesting. We're not going to assess it though, so just be aware of that. Okay, so we want to look at infinite series still, but we want to expand our toolkit as far as what we can use to determine convergence or divergence of a series. And so that's where we're going to start with the integral test. And we've studied geometric series, harmonic series, alternate or telescoping series, right? We already have some tools in our toolkit, but now we want to look at this case where we have the series from 1 to infinity of 1 over I cubed. It doesn't fit any of our previously described models, so what do? Well, can we look at this in a different way? And remember that when we were studying sequences, we said, okay, sequences are really just functions when we restrict our domain to natural numbers. Okay, so does it make sense that we can translate this to an integral and look at the integral and say, well, if the integral converges, does the series converge? And I think it does. If we look at dx over x cubed from 1 to infinity, does that converge or diverge? And well, we saw this type of integral when we were studying improper integrals, but this one ends up converging by what I call P integrals. Okay, P integrals. And if you don't have that theorem handy, here's what it said. We would say, in short, it says the integral from 1 to infinity of dx over x to the p converges if p is bigger than 1, and diverges if p is less than or equal to 1. Okay, so that actually gives rise to what we call the integral test. Because, again, for an integral, we're looking at infinitely many values, right, from 1 to infinity. But when we look at a series, we're not looking at, well, we're looking at infinitely many values still, but rather than looking at all the values in between two integers, we're just looking at the integer, or the natural numbers, I should say. We're looking at just the natural numbers within the domain and the function value corresponding to them. Okay, so here is what the integral test says. Now, we do have to be a little careful. Okay, integral test says suppose f is a continuous, positive, decreasing function. So right off the bat, you have conditions to prove. You have to satisfy all three conditions. It has to be continuous, it has to be positive, it has to be decreasing. So in order to use this theorem, you have to first justify each one of these on a certain domain. Okay, and we're going to say let the sequence an be the function just evaluated at all natural numbers n. Okay, then we would say the series converges if and only if the improper integral converges. Okay, so again, we can view this in two different ways. If we satisfy conditions 1, 2, and 3, okay, then we say the improper integral converges if and only if this infinite series converges and diverges respectively. Okay, so this is going to be the test that we're going to get some practice with in the next video. But again, just to reiterate, and I am saying this again and again and again because we need to make sure to satisfy these conditions. We have to satisfy it is continuous, it is positive, it is decreasing. Okay, and then we can use this test. So let's put it to use in the next video of examples.